All right, so today we'll continue a series of our lectures. And of course, in the previous lectures, uh, we have seen, at least we have been moving from introducing ourselves to certain concepts to the point where we introduce ourselves to certain definitions, certain expansions. Then we went to models, different types of models, the advantages, the disadvantages, and we got to the computational model whilst we introduce ourselves to um, finite state automata. Now we looked at the basic working of any finite state automata, the characteristics, the basic definitions, and we have familiarized ourselves with certain components and the formal definition of a formal model. Today, we continue in that trajectory by going further to look at some other aspects of finite state automata, then other um, improved version of the automaton, what they are useful for, and we look at uh, certain aspects that will be useful to us in subsequent lectures because we're going to be learning certain aspects of automata theory today that would be a foundation to what we'll be doing in subsequent classes and also uh, of introduction. We have learned of certain aspects of automata theory, right? We have been able to learn of the basic definition. We have learned the initial states, the accepting state of final states. We have learned the transition functions. We have learned the symbols and the input strings and all that. So this is just to expatiate further, whilst telling us that several letters can be used to represent any of these states or any of these formalism. So it's not compulsory that we limit ourselves to Q1, Q2, or we limit ourselves to just input. That's the input to be one and zeros. The inputs can be alphabets, the inputs can be or just one and two. So depending on what we define as our input symbol, right, that would be what we'll work with throughout our definition. So a finite state automaton is a machine that is capable of moving. That means transiting from one state to another. So that is one of the most important characteristics of an automaton, the ability to be able to transit from one state to the other. It doesn't just move from one state to the other. There must be an input symbol from a set of alphabets before that transition can take place. So just as the law of motion says that a body will remain at constant rest or it will remain at constant velocity, except an external force acts on it to behave otherwise. So you will remain in a state of inertia except you receive an external force that will push you from the state of inertia to a state of motion. Now, if you look at the latent heat of fusion and latent heat of vaporization in physics, you will notice that water can continue to boil until a certain amount of time comes when the boiling water reaches or gains some certain kind of energy that translates it from the liquid state to the gaseous state. So of course, it's usually I think is MC theta or so to calculate the latency of vaporization. Then the latent feature of fusion is for it to break from that cool nature to the boiling state. So also for automaton, there must be a force or an input that will take it from one state to the other. The first state is usually the initial state. Then we have another state, which is the last state, called the accepting state or the accept state or the final state. Now, upon the receipt of an input symbol from a set of alphabets of a language, so you see the use of words. Now, upon the receipt of input symbols, so the input symbols are set of strings. And last week we said those input symbols must be taken from where? Left to right. And you take one input symbol per time. And those input symbols must come from a set of alphabets. So the set of alphabets to make up the string is usually well defined. Now, if we're going to use three alphabets, it will be defined. If we are going to use just two alphabets, it will be well defined. So it is the combination of those alphabets that form the string that will serve as our input symbol. And this alphabet must be from a language. No, it starts at the initial state and transits from state to state until it gets to the final state or the accepting state. So we can call the final state and accepting state. So we'll be using these words interchangeably. So we use final state or we use the accepting state depending on what we want to drive on. So a final state machine consists of the following. It has a set I called the input alphabet. So remember that the input alphabet defines what can be contained in the string, right? Then we have a set of S whose elements are called states. So we have a global S, which are set of states, right? Just as we use Q in the previous um, lectures. Now a function T, which states that that's when you are in a state S, and upon the receipt of an input function I, you move to another state, and is usually defined as the transition function. Of course, we broke all of these down in the previous lecture. Now, a particular element, which is S naught, which is an element of S, is called the initial state, right? Now, the functioning of the machine is now described in the next slide. So the machine starts in the initial states, which can be represented as S naught. Now, the input is a string or characters from the input alphabet, right? Which are read one at a time from left to right. We asserted this in the previous class. So at each stage, the machine is in some set of S. That means it will be in a state, and that state must be one of the set of states that we have, either the initial state or state 1, state 2, state 3, or the final state or the accepting state. Now, if the machine is in state S and the next input character is C, which is an element of the input string, the machine moves to another state. So you have that so the transition function will be defined that once you're at S and you receive an input symbol C, then you move to another state and wait the next input character after transiting to the new state you find yourself. So the process continues in this way until all the input characters have been processed. Remember, the processing starts from where? Left to right. So upon reading the last input character, right? So once that is done, the next thing is to determine if the string has been accepted or if the string has been rejected. Now, in the previous class, all we did was to see the internal working and how the finite state automaton, how it works generally. However, in this class, we're going to be seeing two. However, in today's class, we'll be seeing um, two forms for which we can represent a finite state automaton. So the first one is called the state table, and the other one is called the transition diagram, called the state graph. So it can be represented as this, which is called the state table, or this, which is called the transition diagram or the state graph, depending on what you want to call it. Okay. So let's look at an example to drive home some of the points we have raised this morning. So we said, given the following, you see now here, these are the input alphabets. The input alphabet here is what? 1 and 2. So all our input symbol will be a combination of 1 and 2 throughout. So it can be 1, 1, 2, 1, 2, 2, 2, 2, and it continues like that. No other alphabet can be in the input string that we're going to pass through the automaton. So given this, we have that our alphabet is 1 and 2, 1 and 2. And our set of states S is what? A, B, C, D. So that makes us that our S naught equals what? A. That means this will be our initial state. Now note that the arrow is used to represent the initial state. So remember that whilst we're dealing with the graphs or the transition diagram, we have that our arrow coming from nowhere and pointing to the first circle or the first state is used to depict what? The initial state, right? So you have an arrow coming to a particular state A. So here, our initial state is A. So you have it represented as this. But on a table, you have the arrow pointing at the initial state. So you see, we have started moving from just our regular circle, right, to transiting it to what? Our circle, to transiting it to a table. So once you see this symbol, this means that this is the initial function or the initial state. Once you are interpreting a state diagram or a transition diagram to a state table. Okay, so please take note of that. So you now see that the transition function is now given as this. So you said you are at A. Upon the receipt of an input symbol 1, you move to B. Then you are still at A. Upon the receipt of the string or the input string 2, you move to C. Now you are done with processing A. Now you are at B. You receive a 1, you move to C. You receive a 2, you move to D. You receive a 1, you move to D. At C, you remove a 2, you move to A. At D, you receive a 1, you move to A. You receive a 2, you move to C. Now let's see how this can be converted to a state diagram. No, a state diagram. So this is a state table. Let's see how this can be changed to a state diagram. Now, the first thing is to get the number of states. So we have how many states? 4 states. So the states are what? A, B, C, and D. So these are the states. State 1, 2, 3, 4. So this is where you get the states. And it's also stated here. So you label them A, B, depends on how you want to label them. It's not compulsory you label them this way. D, right? So the states have been settled. The initial state is what? A. So you put your arrow as A, right? That has been settled. So let's now start reading to draw the symbols or to draw the table. Okay, so it says you are at A, which is initial. You begin from the initial state. You are at A, you receive an input symbol 1. Where do you go to? You go to B. So you said you are at A, you receive an input symbol what? 1. This is the input symbol 1. You move to B. So this is settled. You are still in A, you receive an input symbol 2, you move to C. So you're at A, you receive an input symbol 2, you move to C. So this has been settled, this has been settled. Now here you're at B, right? So put your pen at B. Now you receive an input symbol 1, you move to C. So you receive an input symbol 1, right? You move to C, right? So from B to C, you are now still on state B. You receive an input symbol 2, you move to D. So here, you receive an input symbol 2, you move to D, right? Now you are done with this. Now you're at C now, you are on state C. You receive an input symbol 1, you move to D. You receive an input symbol 1, you move to where? D. Then you are at C, you receive an input symbol 1, 2, sorry, you move to where? A. So you receive 2, you move to A. Then you are now at D, you receive an input symbol 1, you go to where? A. So you can go down, down, down. So you move to A upon the receipt of 1. Then you are at D, you receive an input symbol 2. You move to C. So you can move to C. So it looks clumsy, but if I were to be using a pen or a chalk, maybe a marker, it should have looked a bit, but I'm trying to use my tools here. So what's the label here? You have 2. So you can see if you are giving this diagram or this state diagram to convert it to a table like this, these are the processes you go through in getting that done. And if I give you this table to convert to a state diagram, this is what you go through. So all you need to know is the input alphabet, the set of states, the initial state. Now you notice that on this diagram, we do not have the accept states because it wasn't defined yet in this automaton. So maybe this automaton is just used to process the transition from one state to another without necessarily ending up in an accept state. It's just the transition that we want to model. So that's why I told you in the first class that you do exactly what you are told to model, right? So moving on. So now suppose that still looking at this guy, this table in the previous day, that's what we have moved here. Suppose the input to this machine is this 1 1 2 1 2 2 1 1 2 1. Now the successive transition of the machine as follows. Now look at it very critically so that you follow. So you have that you start at what? Your initial state, which is already written here, A. The first input symbol here is what? 1. So you receive a 1 on the transition. So this is the arrow. Where does it lead you to? Upon the receipt of 1, it takes you to where? B. So that's why you got to B here. Now you are now on state B. The next input string is what? 1. Once you are on B and you receive a 1, where do you go to? It takes you to C. That's why you go to C here. Now you're on C. The next input is what? 2. You pick up a 2. So this is C. When you receive a 2, it takes you to A. So you are at A here, right? Now you are at A, you receive a 1, you go to B. You are at B, you receive a 2, you go to D. You are at D, you receive a 2, you go to C. You are at C, you receive a 1, you go to D. You are at D, receive a 1, and it goes on and until you're able to take the last one, which should be on this arrow, and you get to the last state. However, we have not been told that D is the final state, but it is safe for us to assume that D is the final state and A is the initial state. So that is for a simple transition from state to state, right? So you see that you're on a state A. Upon the receipt of an input function, you transit from that state to another state, and you wait for the next input symbol. So that gives life, or that gives meaning to the definition we have ab initio, where that you are at a particular state, you receive an input function or an input symbol. That input symbol takes you to another state. So all we want to model here is transition from what? State to state. Okay. So that's just a simple um, automaton. Now, milli machine, let's look at another kind of finite state automaton. So to be of any use in computation, a finite state machine or finite state automaton must have some form of output. You see, we're not just moving from state to state now. We want to have a form of output. So how do we get our output? We make use of a milli machine. So the question is, uh, how can we represent a milli machine using a computational model? And this computational model is what? The finite state automata or automaton, depending on how many you are looking at. So you want to print out an output. Before, you just want to move from state to state. However, an obvious way is to have the machine to print out the output. So we need an output alphabet. Now notice, just listen to what I'm going to read out now. We need an output alphabet, O, which is usually big O, that may or may not be the same as the input alphabet. Now listen to that very carefully. Your output alphabet may not belong to the same input alphabet of the string that you are going to use to move to move from state to state. Remember the previous example we have that our input alphabets are what? 1 and 0. But here you are seeing O, a big O. It is not part of that input alphabet. It may be, it may not be. It's just on its own because it's representing another symbol, right? So that may or may not be the same as the input alphabet. So every time the machine reads a character from the inputs, that means the input symbols or the input string, it will output a character as well as changing state. Now look at that definition properly. Every time the machine reads a character, it acts like what? The normal state change, just changing of state, but it adds one more functions again. It will output what? A character. Now, to describe the output of such a machine, we can have an additional function that assigns to each combination of states an input character and output character. In other words, we have a function which is defined, which is P, which is defined that once you are at a state, upon the receipt of an input function, you change state and you also give us an output. So when the machine is in a state S and reads the character C, the output is what? Move to a state and write out an output. So a machine of this type that move from one state and writes an output character is known as a milli machine. So a finite state machine or a finite state automaton of this type is called a milli machine. That's a specific name. However, there are other classes that we can class them in. So the milli machine is of this form. You have that, okay, let's say that you are at S1. This is our S1, right? So it says once you are at S1 and you read a 1, you see this is comma, then output 1. You read, so this is you are at S1. Of course, you can see that S1 is like a final state. Once you're at S1, you read a 1. You read a 1. This is what it means. You read a 1, then you output a 1. That's the first condition. You read a 1, then you print 1, then you move to the next state. And the next state here is what? S3 from the diagram we have. So you move to S3. So this is how we interpret it. You are at S1, right? You read a 1. So you read a 1, you output a 1, and you transit towards S3. That's how you interpret a milling machine, right? And it goes on like that. So here, for instance, this S2, it says once you are an S2, you read a 1, you output a 0, and you remain in S2, right? So this diagram can be represented on a simple table. So let's look at how we can move this state diagram to a state table. Okay, so this is a simple state table for a milling machine. So let's look at how this works. In a regular FS, that's a finite state automaton, you say that if you are at A, you read 0, you go to A. You are still at A, you read a 1, you go to B. That's how for a normal normal FSA finite state automaton is read. However, for a milling machine, what it does is that it says that you are at A, you receive a 0, you output, you get an output 0, and you now move towards A. That's the first one. Now you are at A again, you read a 1, you output a 0, and you move towards state B. So that is how a milling machine works. For every read it does, it moves to a new state and outputs some kind of like a printout. Now, look at this example. So if the input is 11100111, the output will be 0011100011 as shown in the figure below. So we want to test this table and see the output is likely to give. So you're on state A, which is the initial state here. The first one you're supposed to read is what? 1. You read a 1, right? What will be your output when you read a 1? This is a 1. Your output is what? A 0. So this is the output, 0. And you move to where? B. So you move to B. Then this is also, now you are now at B. The next input what is 1. You pick up a 1. Now, this is B. When you read a 1 under B, you get to D. Now, what's the output of 1 under the output? 0. So you have your 0 output here. So you are now in D, right? So you are on D now. You read the next input, which is 1, which is this. You output, so this is D. Upon reading a 1, you output a 1, which is this. And where does it take you to? Under 1, you have to be in D. And that's where you are still on D. So it continues like that until you read all of these input symbol. Okay. So there's another way by which we can also print out or output maybe character upon changing of state, and that is a different machine on its own, and the machine is called the Moore machine. So the first one is the milling machine, that once you receive an input symbol, right, you output an output symbol and you change your state. But for the Moore machine, it operates in a different way. So an alternative arrangement for output is to have the machine print a certain output character as it enters a state. So these machines are called Moore machines. So the output, the only difference is that the output is attached to the state rather than the transition. So the output is usually on the state, right? So let's say this is state A, then the output, let's say the output is 1, is attached to it. Let's say this is state B, the output is attached to state B, depending on what you want to output. So the input symbol will just go. Maybe this is 1. So you now have stroke something as output. So the output is attached to the state. Now the output is attached to the state rather than the transition. So formally, the output of a Moore machine is described by the function P that you are in a state, you print out an output. Whereas before, O is the output alphabet. So the following Moore machine is also a two-step delay, right? The following Moore machine is also a two-step delay. So we can use FSA to be a delay model, behaving equivalent to a milli machine in the example above. So this, you have that your input symbol is also the same as your output symbol, which is zeros and one. The states are what? A, B, C, D. What is the initial state? A, right? So we look at the state table below and try to pass the following set of inputs: 11100001111. Now you see, this is a Moore machine. This is a table of a Moore machine. Now, what is the difference? The difference is that we do not have double outputs. Why? Because the output is attached to the state. So here you have your A slash 0. B will also be attached to 0. So you have them this way. So your F will be what? Attached to 1. Your G will also be attached to 1, and it continues like that. So all you need is just to moving from state to state and giving us a set of output. So let's look at it. Say we should pass this in this Moore machine. So your initial state is written. The first input string that you pick up is what? 1, right? So once you pick up a 1, you move to where? State B, and you output what is in state B. Now you're an A. Okay, so you're on state A, you read a 1. This is 1. It takes you to B. And that's why you have gotten to B here. Now, what is the output of state B? Is this 0. So you put the 0 out here. Now, you're on state B now. You read the next 1. This is state B. When you read the 1, it takes you to D. So this is the D. Now, what is the output of D? 0. Now, you're on state D now. You receive the next one, which is 1. This is 1. It takes you to, this is D, right? That's under 1, you have your H. So you go to state H. The output of state H is what? 1. So you send out your output. You're on state H, you pick up the next input, which is 0. So this is H. You pick up a 0. It takes you to G. You are now on G. The output of G here is what? 1. You get up 1. So it continues in that regards until you're able to fit symbol. Then also the output, the big output of that input set of input string that you have, right? So that is the operation of a milli machine and a Moore machine. For a milli machine, on your transition, you send out an output and move to a new state. However, for a Moore machine, you pick up an input, you go to a state, and you output without necessarily putting your output on the transition line. Okay, so finite state acceptors. So the focus of finite state machine will be as acceptors. Of course, we have looked at that last week, where we say that if you test some input string, it must, it must get to the final state, right? That is the whole essence of a finite state acceptor, not a finite state automaton. So the focus of a finite state machine will be as acceptors for languages. Now, given a language on a given alphabet, it is important to find a machine that decides whether or not a given string belongs to that language. So given a language on a given alphabet, it is important to find a machine that decides whether or not a given string belongs to that language, right? Of course, we have done a bit on this in lexical analysis, where you scan through the whole program you have written in high level language. You check that, oh, can you produce tokens and can you produce tokens from the lexeme that you have found in the whole program that you have written, right? So finite state automaton can also help in this regard. You create certain lexeme, you identify them as, you give them a form of identifier. Maybe, okay, this is an identifier, this is a an operator, right? This is an operand, and it goes on and on. So here, the output is simple yes or no. So we're not interested in partial results, right? We're not just going to stop halfway. If it gets to the accept state, then good. But if it doesn't, then we say it is rejected. We wait for the machine to read the entire input string, and only then are we interested in the answers. So we're not interested in the answers during the movement from point to point. We're not interested probably in the transition function. We're only interested if the transition function has completed maybe the consumption of the input strings, right? Then at that time, we now come, okay, you have read the last input string. Where is your position? Are you on the initial state? Are you in the intermediate state? Or are you on the final state? It's based on that we can now give our verdict. So if a finite state acceptor, that's in a finite state acceptor, the output is determined by selecting a subset of states as the accepting states or final state. So we can have accepting state and final state, as I said. So if the machine ends in an accepting state, after having read the entire string, we say that the string has been accepted by the machine. Otherwise, it is said to have been rejected. So the slight modification to the way we present it as a finite state acceptor on the table is to replace the ones in the final column by asterisks. Now, this line is very important for subsequent chapters we are going to be looking at. We want to see how a finite state automaton can be represented as a finite state acceptor. So what do? We look at the final state or the accepting states, and we represent them with what? An asterisk on the table. Then those ones without those that are not final states, or those are not accepting states, we just leave them blank. So each time you see an asterisk in front of a table, right? In a state that's in front of a state on a table, you know that that state is an accepting state or a final state. So that the accepting states are those with an asterisk against them. So rewriting the Moore machine in the example above as a finite state acceptor, we have this diagram, right? So this is what we are rewriting, this diagram here, A to H and here. So what does this state? Now look at this. So these are accepting states with ones in front of it. They are the accepting states. These are not accepting states. So what do? Instead of putting 1, 1, we just put asterisk here. And this one goes asterisk here, asterisk here, asterisk there, right? So that's, we have written our finite state acceptor in this way. So if you see this one, we have our asterisk, our asterisk, our asterisk, and asterisk. That means E is an accepting state, F is an accepting state, G is an accepting state, and H is also an accepting state. So the main focus will be on finite state acceptors. So going forward, we are going to be looking at finite state automatons that are acceptors, right? To every FSA, there is a language. Excuse me. The set of all input strings that are accepted by this machine. So we say that an FSA accepts a language L if it accepts every string in L and rejects all others. An important question is, can every language be accepted by an FSA? The answer is no. Only for certain languages does there exist a corresponding FSA. So let's now look at state diagram. Of course, I've been mixing it up, teaching and coming back. So it is convenient to depict a finite state machine pictorially. This is done by drawing a circle, a small circle for each state with the name of the state inside. So you have maybe state A. This is draw a small circle with the name of the state inside. So this is done by drawing a small circle for each state with the name of the state inside and drawing arrows connecting the state to depict the transition. So this is A. Let's assume that this is now B. So when we have an arrow like this, a directional arrow, there's always an arrow telling, okay, this arrow is going from A to B. If it is coming from this way and the arrow is pointing here, that means it's coming from B to A. So, I'm drawing arrows connecting the states to depict the transition. So the input character that gives rise to a transition is written beside the corresponding arrow. So if you read A1, this is the input character. If you put a 0, this is the input character. So we indicate the initial state by drawing a short arrow pointing to it. So we just put here, this is what? The initial state using a small arrow. Of course, we have learned this already, but this is just putting it into proper perspective. Okay. So output is depicted in the following way for different machines that we have. So for the output of a milli machine, it says that once you're on A, state A, you receive an input alphabet of 1, you output a 0, and you move to state G. You see, I'm speaking English now, but these are just models, right, to depict what I've just said. So what does it say it again? You are on state A, that is English language. You, upon the receipt of an input alphabet 1, you output a 0 and you make a transition to state G and remain there. So this indicates that if the machine is in state A and receives an input 1, then it outputs a 0 and moves to G. So if I just put only this and tell you to interpret it using pure English, you should be able to do that. So if I give you several links of this, interpret it in plain English, you should be able to do that. Okay. So for more machine, so the output is attached to the name of the state as follows. So here you are on state A, you receive an input symbol 1. You move to state G and output is 0. So this indicates that if the machine is in state A and receives an input 1, it moves to state G and output 1. The previous one is that once you're in state A, you receive a 1, you send out an output first before you move to a state. But here, you move to the state before sending out the output. So for an FSA, the accepting states are distinguished by drawing a double ring around them as follows. So this is state A, which is just a normal state. This is a state G with double circle, telling us that it is an accepting state. And the input alphabet is what? 1. So this indicates that if the machine is in state A and receives input 1, it moves to state G. Now, if that was the last character that we are reading on the input string, the string would have been said to be what? Accepted. So these are the different transition and of course, how to interpret some of these FSA, milling machine, mold machine, and all. All right. So the following tables and diagram represent the same milling machine. Remember, milling machine says that you are on a state. You pick up an input. So this is the input, this is the output, and you move to a state. So if you look at this is what it says. You are at A, state A, you receive a 0. So if you receive a 0 here, where do you go? You go to B. Here, you go to B, and what will be your output? Your output is 1. You are still on state A, you receive a 1, right? You move to state C, and that's where you have moved to, and your output is 0. Your output is 0. So that's how you interpret each of those diagrams. Ditto for this. So for a more machine, right, you are on state A, you receive a 0, you move to B, and you output a 1. You're on state A, you receive a 1, you receive a 0, you move to B, and you output a 1. It also follows for the other states. Then the next one is for a normal FSA. It says that this A is an initial state and also what? An accept state, an accepting state. This is also an accepting state. This is also an accepting state. So that's why you have them having what? Double circle. So it says once you're on A, you receive a 0, you move to B. You're on A, you receive a 0, you move to B. Now you are still on A, you receive a 1, you move to C, and ditto for the other states. How? So that is that about the introduction. So what is important for you to note is this representation for accept states. Remember, this on the table would have been what? 1, 1, 1, 0. But because we have introduced this this formalism, so going forward, anywhere you see 0, this star means that it is a 1. Anywhere you see these stars and there's nothing in front of another, that means it's what? A 0. Okay, so let's go to another concept called the concept of black hole. So with an FSA, we often arrive at a situation where we can reject the entire string without needing to see what other things we are supposed to read. Now, for example, if we have an acceptor for this language, you see that star, what's the star? What's the name of that star from what we have done before? That's the clean star, right? And what is the clean star all about? As much as this, but in this direction. So here will be, we have 1, 0, 1, 0, 1, 0, 1, 0, maybe in multiple numbers. So we can reject the string 1, 0, 1, 1, 0, because that has violated the arrangement that that clean star has defined. So you see the first one, uh, the first one obeys the law, which is 1, 0. The second one should also be what? 1, 0, but it didn't. It brought 1. So this has been rejected because this language will not be accepted by the automaton because it doesn't follow the required 1, 0, 1, 0, 1, 0 that has been defined by this language. So beyond this point, we do not care what we read. The fate of the string is already sealed. So the most convenient way of dealing with this is to have a special state that represents rejection before the input is complete. So the transition coming out of such a state should lead right back again. Therefore, once the machine gets into this state, it can never get out, right? So that's why we call it a black hole. For this reason, it is sometimes known as the black hole by analogy with this region of outer space with such a high concentration of gravitational force that nothing that enters can escape. Um, yeah. So it's represented like this, such that if This is the black hole. Anything that goes in doesn't just come out of it. Anything that goes in doesn't come. So we're going to see the importance or the notation why we need to have a black hole and why black hole is also important. So a typical FSA will have a black hole. Only one is ever necessary with many transition into it. So this coming. So to include the black hole in a state diagram with all its entering arrows will make the diagram look excessively clumsy. So for this reason, we generally omit the black hole from state diagram, but it is present. It is assumed to be present. So we're going to be looking at what a black hole is, how it is assumed to be present, and how we remove it after we have taken care of all the contingencies. Therefore, whenever there is no arrow emerging from a state for a particular character, it's assumed that there is an invisible arrow leading to that black hole. Now, listen to that carefully. Say, therefore, whenever there is no arrow emerging for a state, from a state, for a particular input character. So let me explain. Now, you have a state. Let's say this is state A. Normally, you are supposed to have an input going out on the input character of what? 0, and another going out on the input character of 1. But you find out that at times, you just have just one of these, maybe just one going out of A without a corresponding value of 0. So on this point, you cannot read a 0. So it doesn't go anywhere. It's just a waste of time. So let's assume that we have, let me clean this. We have this. Okay, so you have this A. So you want to pass this 0, 1, 1. So if you read this, let's assume that this is not available. So by the time you read 0, this automaton will not even move from A to anywhere because it doesn't have anywhere to read a 0. So you can't go anywhere. You just get stuck here. So instead of us having this to go we clean it, we just direct it to another place. Let's say F, and we say this F is the black hole, so that by the time you read 0, you just go straight to what? F, and you cannot escape. So any other thing after it cannot be read because it has not carried us to a state where we can make use of the next input string. So we stop at that instance and we say, okay, that language is rejected at that point. So therefore, when there is no arrow emerging from a state for a particular input character, it is assumed that there is an invisible arrow leading to the black hole. And of course, the black hole is never an accepting state, or it's not a final state. Okay, so design an FSA to accept the language consisting of all binary string that begins with what? 1011. In other words, design an FSA for the language given by the regular expression 1011 and any other addition of 0 plus 1 in that movement. That means, this clean star, we have defined what the clean star is. So there's no need for me to start teaching what the clean star is and how the expansion is done. So what is the solution to that, right? The first thing you are told to do is to design a language that will accept this string. So if you look at it, you just draw the transition. This is just draw your states. You just continue to draw your state. So you start with drawing the first state. So let's assume that the first state is A, right? You pick up this input symbol as what? 1. You move to the next state, which is let's B, right? The next input what is what? 0. 0. You move. Then let's C. The next input symbol is what? 1. You put 1. Then D. The next input symbol is what? 1. So 1, and you go to where? E. So this is the end of the input string, right? So you can put it on the double arrow. Then it now says either 0 or 1 can also be needed here. So you put read 0, 0, comma 1, or you just put read 0, read 1. So you can see that with this language, you can know how many set of states that you will need. Now, if you look at this now, only 1 goes out of A, whereas the other input gone, which is supposed to be 0, it will go into what? Let me clean so that we'll be able to understand. So these are the inputs, well, 1, 0, 1, 1, and this is the accepting state. Then plus 0 or 1, so 1 or 0. Now, for the first one, only one input symbol can leave A, which is 1. There should be another one, which is a function, which is an input of 0. So this automatically goes to what? The black hole. For B, only 0 goes out of it, but there should be another corresponding output because it's defined in the alphabet of that string. So B goes to the black hole. Here, B1 goes to black hole, C0 goes to black hole, D0 goes to the black hole, and like that. Now, in order to now make your diagram very tidy, you just remove all of this because it is not really necessary. Because you can't go anywhere with all of this. So you just remove all of this and just represent your diagram using only this. So what do you have? You have the state F is clearly acting as a black hole. Therefore, we can simplify the diagram by deleting it. You see here, we have deleted that black hole where you have all of these moving to it, right? So it has been deleted already, right? So any transition that are not shown are assumed to lead to the black hole. Another simplification is to combine arrows that start and finish with the same state. But of course, you see, we have looked at where the black hole is and the removal of same. So notes. So notes, just a bit, clean out this. Okay, notes. Do not confuse this, right? Do not confuse 0, 1 with the notation of input and output where we have in the what? In the more machine. No, in the milli and more machine that we use in milli machine. Some books use 0, 1 in such situations. So there is some danger of confusion. So for us, we shall use 0 or 1, which means read is 0 and write an output of what? 1. While 0, 1 means read either 0 or 1 at a time. Note that E here is not a black hole, right? Because it is an accepting state. We will meet a black hole in a state diagram, but it must be included on the state table. Now, please take note of all these basic laws because they are going to be pivotal to our learning in subsequent classes. So what are the applications of DFAs? That's when we say DFAs, that's deterministic finite state automata or finite state automata in lexical analysis. So the DFA can be implemented as a table-driven or hand-coded scanner. Of course, we have looked at scanners and we have looked at parsers, right? So table-driven scanner are usually generated by some specific tools like Flex. Now, because with DFAs or finite state automata, each input uniquely determines the state to navigate to, and it never backtracks. It never backtracks. The DFA is the preferred model for the implementation in generated scanner. So that means the finite state automaton can be used as a computational model for a simple scanner. Especially that's, of course, the scanning is the lexical analysis part of compiler construction. So the usual flow consists of converting a lexical specification, either regular grammar or regular expression, um, into NFA, and then NFA is converted into DFA. Of course, we're going to be looking at what NFA is, which is non-deterministic finite state automata. And of course, what we are looking at now is also known as what? Deterministic finite state automata. Deterministic in the sense that you take one input and you know the next place you are going. But the non-deterministic is that you don't even know. You take a one input and the possible set of transition can be many. So probably you'll need to cast a lot to say, okay, where do I go from this place? So here is a picture, is the picture that demonstrates that workflow. So you have the regular expression or the grammar, you have the lexical specification converted to non-deterministic finite state automaton. You normalize the finite state automaton to a deterministic finite state automaton. And remember, we say we create a what in compiler, we create an intermediate representation, and that's the NFA. Then we optimize. So when we optimize, we can now get a table driven implementation that will be easy for us to target to any microprocessor. So however, most commercial and open source compiler use hand-coded scanner. Such scanner is faster than a generated scanner because during implementation, some overheads that is necessary in a generated scanner can be removed. So when writing an hand-coded scanner, usually there's no need for the explicit conversion of grammar or reject to a DFA, since it is possible to implement the scanner algorithm manually directly from the lexical specification. Such hand-coded implementation naturally ends up working like a deterministic finite state automaton. So both table-driven and hand-coded scanner function, both table-driven and hand-coded scanner functions in the similar way by emulating the deterministic finite state automaton. Of course, you are going to see the difference between deterministic finite state automaton and non-deterministic finite state automaton. Then how to convert a non-deterministic finite state automaton to a deterministic finite state automaton. Of course, we are going to look at the steps when we are done with equivalence and reduction. So after reading an input, the scanner checks whether there are possible transitions using the input. So if the transition is found, it is followed and the scanner ends up in a new state. Now, if there are no transition available, the scanner checks if the current state is the accepting state. That means if you write your code in high-level language, it checks, are there other lexemes? Are there other tokens I can create? So if it has read through and that's the last thing you have written, you say, oh, that means this is the last thing that I found in scanning through this whole length of code. Then it assumes that, oh, it's in the accept state. So if that's the case, the scanner recognizes the word and returns a lexeme, right? And its syntax category to the calling procedure. Otherwise, scanner determines whether or not it has passed through an accepting state on the way to current state. So that means this is explaining what is the difference between a pass and a face, right? So if it has maybe you wrote something like set, and you know set is a reserved word, kind of. Now, if it has taken that set as a variable and it has said, oh, this is classified as an identifier, if it now goes to its reserved word and say, oh, so set is a reserved word, it goes back to that place that, oh, hope I've not made a mistake, right? That's okay. Let me retrace myself to say, after reading all this, it doesn't make sense. So let me see if I can retract and make a bit of sense. So you'll be looking at that in what? Your DFA and, oh no, in your NFA, right? Now, the good thing about NFA is that irrespective of the decision you are supposed to take in a particular state where you have several other states to visit, you just need one of the states to get to the accepted. And if one of the states gets to the accepted, you don't care what happens to the rest of the states, right? But for a DFE, just one state moving to the next up until you get to the accepting state. So otherwise, it reports an error. So that is the end of today's class. On at least we have deepened our understanding of automata theory and the finite state automaton. We have looked at what an accepting state looks like. We have looked at what a milling machine looks like. We have looked at what a Moore machine looks like, how they operate, and of course, what improvement they have brought on computational models, right? Then maybe in the next class, we are going to be looking at equivalence, reduction, and standardization. Then after that, we end with NFAs to DFAs. When we introduce ourselves to what NFAs are, then what DFAs look like. So those are the things we'll be looking at generally. And I hope at least you follow as we go. So this is the end of today's